March 1916. A Canadian mining engineer watched British soldiers dying from exposure in the mud. He grabbed some abandoned metal sheets. 6 soldiers who'd never built anything in their lives. 72 hours later, they had a building. 26 years later, American engineers tried to improve his design. They made it worse. This is the story of 2 metal huts. One was designed during artillery bombardment by a man who had no architecture training. The other was designed in peacetime by America's best military engineers with unlimited resources. One could be built by exhausted infantrymen in 3 days using only hand tools. The other took 10 days and required specialized equipment. One cost $230. The other cost $850. And here's the strange part. The expensive one that took longer was considered the improvement. But when it mattered most, when soldiers were dying and bombs were falling, armies kept wishing they had the simpler one. Lieutenant Colonel Peter Norman Nissen wasn't an architect. He was a mining engineer, born in Canada, working with the British Royal Engineers in France during World War I. And in early 1916, he had a problem that was killing men faster than German bullets. The Western Front had completely destroyed traditional building methods. Think about what armies needed. Shelter for hundreds of thousands of troops, hospitals for the wounded, supply depots, command posts, workshops. All of it had to be built quickly, had to withstand shelling, had to use materials that were actually available. Timber was scarce. Every tree in northern France had already been cut down for trench supports. Skilled carpenters were in the trenches fighting, not building. And every day men were dying from exposure. Pneumonia killed more soldiers than you'd think. Guys surviving battles only to die shivering in canvas tents that collapsed under snow. Nissen walked through the muddy construction sites near Ypres and noticed something strange. Piles of corrugated iron sheets just sitting there, abandoned near supply depots. These curved metal panels, originally meant for roofing, were stacking up because nobody knew what to do with them. Meanwhile, men were freezing to death in tents 50 yards away. He looked at those metal sheets, then he looked at the men, and he had an idea so simple it seemed stupid. What if you just bent the metal into a half circle? No frame, no supports, just curved metal bolted together. The shape itself would be the structure, like an upside-down boat hull made of corrugated steel. Most engineers would have dismissed this immediately. You can't build like that. You need vertical walls. You need a frame to support the roof. You need foundations. You need skilled labor. But Nissen wasn't thinking like an engineer. He was thinking like a soldier. And soldiers don't need perfect. They need fast. March 1916. He assembled the first prototype at Ypres. 6 soldiers, none of them had ever built anything in their lives. They used standard-issue tools, wrenches, hammers, bolts, that's it. The structure went up in less than 4 hours. 4 hours! From pile of metal to weatherproof building. No foundation, no frame, just curved corrugated sheets bolted together with wooden end walls. When Nissen presented his design to British Army Command, he made one promise that changed everything. Any infantryman with basic instructions could build it in 3 days. And all the materials could fit on a single truck. The British Army tested this immediately. April 1916, Richborough Port. The 172nd Tunneling Company erected 20 huts. Each hut was 16 feet wide, used about 600 square feet of corrugated steel. The curved design meant rain and shrapnel slid off instead of penetrating. And because there were no vertical walls, there were no weak points where shells could catch and tear. 3 days per hut, with completely inexperienced crews. By June 1916, Nissen huts were appearing across every British sector of the Western Front. The War Office placed a massive order in August, 10,000 units before winter. And here's what made this revolutionary. It wasn't the metal, it wasn't the shape, it was the elimination of skilled labor from the equation. Traditional military construction required carpenters, masons, engineers. Nissen's design needed none of that. The corrugated sheets came pre-drilled with holes spaced exactly 14 inches apart. Wooden end walls arrived as prefabricated panels. The foundation was optional. Crews could bolt the hut directly to wooden boards or even to packed earth if necessary. A sergeant and 5 privates could unload the materials, lay out the base, and have the structure weatherproof before nightfall. During the Battle of the Somme in late 1916, construction units were erecting Nissen huts within artillery range, providing immediate shelter for wounded men being evacuated from the front lines, while shells were still falling. The dimensions were calculated for maximum efficiency. 16 feet wide allowed 2 rows of bunks with a central aisle, housing 30 men comfortably, or 50 in emergency conditions. The curved roof rose to about 15 feet at its peak, enough vertical space that men could stand upright in most of the interior. Ventilation came from adjustable panels at each end, and the corrugated steel's natural air gaps prevented the condensation problems that plagued canvas tents. By November 1918, when the war ended, British forces had deployed over 100,000 Nissen huts across Europe, the Middle East, Africa. They served as barracks, hospitals, supply depots, command posts, anywhere the Army needed instant infrastructure. The construction sequence was intentionally foolproof. Step 1, lay wooden base plates in a rectangular outline. Step 2, bolt vertical wooden ribs to those plates at 7-foot intervals. Step 3, attach the first corrugated sheet to the ribs and bolt it to the base. Step 4, add the next sheet, overlapping and bolting it to the first. Repeat until the half cylinder was complete. Step 5, install the wooden end walls, which came with pre-hung doors and window frames. Total assembly time, with an experienced crew, 72 hours. With completely green troops who'd never seen one before, 4 to 5 days. The British Army tested this repeatedly at training camps throughout summer 1916, timing different units to establish reliable deployment schedules. What separated the Nissen from everything that came after was its relationship with available materials. Nissen designed around what Britain could actually produce under wartime conditions. The corrugated steel sheets were 26 gauge, thick enough to resist damage, but thin enough that 3 men could carry a section without mechanical assistance. The curve radius was precisely calculated so that standard sheet metal rollers at British factories could form the shape without retooling. Every bolt was 7/16 inch diameter, the same size used in ship construction, meaning supply chains didn't need special inventory. The wooden components, end walls, base plates, interior ribs, came from whatever timber was available: pine, oak, even salvaged wood from damaged buildings. Field adaptability made the system nearly universal. In Mesopotamia, during 1917, British forces built Nissen huts without the wooden end walls, instead using bricks scavenged from ruined villages. In Egypt, engineering units set the bases directly on sand and used interior poles cut from local palm trees instead of milled lumber. The core principle remained. Those curved, corrugated sheets would form a weatherproof shell regardless of what you did with the rest. A Canadian unit at Vimy Ridge in March 1917 erected a Nissen hut during active bombardment, working in 30-minute shifts between artillery barrages. The structure was operational within 18 hours, immediately housing 40 wounded men evacuated from the ridge assault. The speed advantage became most obvious in logistics. A single railway flat car could transport enough materials for 8 complete Nissen huts, 48 sheets of corrugated steel, wooden components, hardware. At Étaples military camp in France, construction teams maintained a record pace throughout 1917. One completed hut every 6 hours when working in rotation. By October 1917, Étaples had grown to accommodate 100,000 troops, almost entirely housed in Nissen structures. The camp's hospital section alone contained 300 huts, providing bed space for 12,000 patients. When the German spring offensive hit in March 1918 and suddenly 20,000 additional wounded needed shelter, crews erected 70 new hospital huts in 11 days. 11 days for 70 complete buildings, housing thousands of wounded men, while the front line was collapsing 50 miles away. Fast forward to September 1940. The United States Navy sent an engineering assessment team to Britain, 15 months before Pearl Harbor. Commander George F. Dora, stationed at the Bureau of Yards and Docks in Washington, had explicit orders: study British temporary construction methods, determine if they could support American military expansion. Dora spent 6 weeks touring RAF bases, Army camps, Royal Navy installations across England and Scotland. His classified report, filed in November 1940, devoted 18 pages to the Nissen hut. He documented assembly times, material specifications, interviewed British construction officers who'd deployed them since 1916. Dora's conclusion was direct. The Nissen hut was the fastest field structure ever designed. But American forces would need modifications. Modifications. That word. That's where everything changed. December 7, 1941. Pearl Harbor. America was at war, and the modifications began immediately. The Navy Civil Engineer Corps chose Quonset Point Naval Air Station in Rhode Island as the development site. Commander John Barney Cyrus led the design team, working with specifications Dora had brought from Britain, along with actual Nissen hut blueprints the British government provided under Lend-Lease arrangements. February 1942. The first American prototype emerged. It looked similar to the Nissen, but it carried fundamental differences that would affect every single unit built thereafter. American engineers changed the structural logic. Where Nissen used corrugated sheets as self-supporting elements bolted directly together, the Quonset design introduced an internal steel framework. This framework consisted of curved steel arches, essentially ribs made from formed steel channels that stood independently and supported the corrugated panels. The panels no longer carried structural loads. They were cladding, attached to the frame with self-tapping screws rather than through bolts. Cyrus argued this approach would create stronger buildings, capable of supporting heavier equipment loads, providing better anchor points for electrical and plumbing systems. He was correct on both counts, but he'd introduced a complexity the Nissen deliberately avoided. The framework requirement meant Quonset huts arrived at deployment sites as more components, requiring more assembly steps. A standard 40-foot Quonset needed 14 steel arch ribs, each weighing approximately 90 pounds, positioned at specific intervals and bolted to foundation plates. Only after the frame was complete could crews attach the corrugated panels. Nissen assemblies started with the panels themselves and built outward. Quonset assemblies started with an invisible framework and worked inward. This philosophical difference, framework first versus panels first, added between 12 and 18 hours to construction time, based on tests conducted at Quonset Point in March 1942. Navy officials accepted the trade-off because they prioritized building permanence over deployment speed. American planning doctrine assumed most bases would be occupied for years, not weeks. The Quonset also incorporated features absent from the Nissen design. Interior insulation became standard. Blankets of fiberglass sandwiched between the steel panels and interior plywood lining. Electrical conduits were integrated into the framework during assembly, rather than surface-mounted afterward. Wooden floors replaced the Nissen's packed earth or wooden duckboards. Windows were larger and included screens. Doors used American standard hardware instead of British hinges and latches. Each improvement made sense from a comfort and functionality standpoint, and each added weight, components, and assembly time. A complete Quonset hut package weighed approximately 30% more than equivalent Nissen materials, requiring more trucks or rail cars for transport. By May 1942, the Navy had standardized 3 Quonset sizes: 20 feet wide, 40 feet wide, and the largest at 50 feet wide. Production contracts went to the George A. Fuller Company and the Strand Steel Corporation, both experienced with prefabricated steel construction. The first mass-produced units shipped to naval stations in June 1942. The steel framework that defined the Quonset created a parts dependency the Nissen never had. Each arch rib arrived as a preformed piece of steel channel bent to the precise radius needed for that particular hut size. If one rib was damaged during shipping, bent, cracked, or missing bolt holes, the entire frame's geometry could fail. Nissen huts tolerated imperfection because the corrugated panels flexed and adjusted as crews bolted them together. The panels themselves corrected minor alignment errors. Quonset ribs had to align perfectly before any exterior panels went on, which meant construction crews spent hours using levels, plumb lines, and measuring tapes to ensure every rib stood at exactly 90 degrees to the foundation and matched the spacing templates. The bolt count told the story of increasing complexity. A 16-foot Nissen hut used approximately 200 bolts total, mostly connecting corrugated panels to each other and to the wooden base. A 40-foot Quonset hut required over 700 bolts and screws. 14 arch ribs, bolted to foundation plates, used 6 bolts each, totaling 84. Cross-bracing between ribs added another 100 bolts. Attaching corrugated panels to the framework with self-tapping screws meant 16 screws per panel, and a 40-foot Quonset used roughly 30 panels. Then came the interior work: plywood lining attached to the ribs, insulation fasteners, electrical box mounts, floor joists bolted to the foundation. Every additional fastener was another opportunity for construction delays. When tools broke, when hardware went missing in the field. American production methods emphasized standardization that paradoxically reduced field flexibility. Quonset components were manufactured to tight tolerances in stateside factories, which ensured pieces fit together perfectly under controlled conditions. But combat zones weren't controlled conditions. January 1943, the 804th Engineer Aviation Battalion arrived at Henderson Field on Guadalcanal. They discovered that humid conditions had caused some steel ribs to rust at bolt holes during the Pacific crossing. The ribs couldn't be modified or replaced with local materials because the entire structure depended on those precisely formed arches. The engineers had to wait 3 weeks for replacement ribs to arrive from Pearl Harbor, while troops slept in tents. The insulation system, while providing superior comfort, became a construction bottleneck. Quonset specifications required fiberglass batting to be installed between the exterior corrugated panels and interior plywood lining. This meant crews had to work in 3 stages: erect the frame, attach exterior panels, then go back inside to install insulation and interior walls. Nissen huts were single-stage construction. Once the corrugated panels were up, the structure was complete and habitable. Interior improvements came later if time and materials allowed. At the Navy's Camp Endicott in Davisville, Rhode Island, where Seabee battalions trained in 1943, instructors timed both systems. An experienced crew could complete a Nissen-style hut in 48 hours. The same crew needed 96 hours for a comparable Quonset with full insulation and interior finishing. Electrical integration added another layer of pre-planning that slowed field deployment. Quonset huts came with conduit pathways built into the framework, which meant electricians had to work simultaneously with construction crews, rather than after the structure was complete. At naval air stations with abundant electrical contractors, this parallel construction worked efficiently, but in forward combat zones with limited personnel, having electricians occupy the work site while structural crews were still bolting ribs together created scheduling conflicts. The 6th Naval Construction Battalion in the Solomon Islands reported in April 1943 that electrical requirements delayed average Quonset completion by 2 full days because qualified electricians were rotating between multiple construction sites. The floor system represented perhaps the most significant speed penalty. Nissen huts had no integrated floors. Troops laid wooden duck boards or poured concrete after the structure was up. Quonset specifications required pressure-treated floor joists, plywood subflooring, and finished wood flooring, all installed during initial construction. This kept the interior clean and comfortable, but added an entire phase of carpentry work. November 8, 1942, Major General George Patton's Western Task Force landed near Casablanca. His supply officers carried orders for immediate camp construction to support 35,000 troops. The invasion plan allocated space for Quonset huts shipped from Virginia, but combat conditions forced field commanders to make calculations the Navy hadn't tested at Quonset Point. Lieutenant Colonel Paul Thompson, commanding the 16th Engineer Battalion, watched his crews struggle with the steel framework in sand that wouldn't hold anchor bolts. The foundation plates designed for firm ground or concrete pads twisted when tightened, because Moroccan coastal sand compressed unevenly. Thompson's after-action report filed in December 1942 noted his crews needed 4 days per Quonset hut, with most time loss stabilizing foundations and shimming framework ribs to compensate for uneven settling. British forces at the same North African theater were simultaneously deploying Nissen huts they'd shipped from Alexandria. The 512th Specialist Team Royal Engineers set up a field hospital outside Algiers starting November 12, 1942. Working with local Algerian laborers who spoke minimal English, the team completed 16 Nissen huts in 9 days. Their technique eliminated foundations entirely. They laid railway sleepers directly on graded sand, bolted the corrugated panels to those sleepers, and stabilized everything with sand berms piled against the exterior base. When windstorms hit in late November, several Quonset huts under construction toppled because their frameworks weren't yet clad with panels. The Nissen structures, already complete with their self-supporting shells, stayed standing. The Pacific Theater exposed even starker differences. Guadalcanal. The 1st Marine Division began receiving Quonset huts in February 1943, after months of fighting in muddy tent camps. Gunnery Sergeant Robert Lakey, whose memoir documented the campaign, described watching construction crews work in 100-degree heat with 80% humidity. The steel framework components were too hot to handle with bare hands by mid-morning. Crews worked abbreviated schedules, dawn until 10 a.m., then evening until dark, which stretched 5-day construction estimates into 2-week realities. Meanwhile, Australian forces supporting operations from Port Moresby used Nissen pattern huts manufactured in Sydney. Australian war production records show these simplified versions eliminated even the wooden end walls, using corrugated steel throughout, and construction teams reported average assembly times of 36 hours. Timing mattered most during rapid base expansion. March 1943, Admiral Chester Nimitz ordered the development of Funafuti Atoll in the Ellis Islands. Navy planners needed housing for 5,000 personnel within 60 days. The 2nd Naval Construction Battalion arrived with both Quonset materials and some British Nissen huts acquired through Commonwealth supply channels. Battalion Commander Lieutenant Commander Joseph Blunden split his crews to test both systems under identical coral atoll conditions. His official report in May 1943 provided exact figures. Nissen huts averaged 54 hours from first foundation timber to completed structure. Quonset huts averaged 91 hours, with the gap attributed primarily to framework alignment and interior finishing requirements. The speed differential became critical during emergency expansions. After the Battle of Midway in June 1942, the Navy needed immediate hospital capacity at Pearl Harbor for incoming wounded. The existing hospital couldn't accommodate the surge, so construction battalions erected temporary ward buildings adjacent to the main facility. Using Quonset huts with their required foundations, frameworks, and interior systems would have meant a 2-week construction timeline. Instead, crews used a hybrid approach. Nissen-style corrugated shells erected in 3 days with interior medical equipment installed afterward. Those emergency wards remained in service through 1944, housing over 2,000 patients during their operational period. Weather resistance revealed unexpected trade-offs. Quonset insulation kept interiors comfortable in extreme heat and cold, but the complex wall assembly created moisture traps. In the Aleutian Islands during 1943, where fog and rain were constant, insulated Quonset huts developed condensation between the exterior steel and interior plywood, leading to rust and mold. Nissen huts, with their single-layer construction and natural ventilation through corrugation gaps, stayed drier, despite being less comfortable. Cost accounting revealed where American engineering priorities diverged from British expediency. In 1943, a complete 40 by 20 Quonset hut cost the Navy approximately $850, including all materials, hardware, insulation, electrical components, and flooring. A comparable Nissen hut, based on British production records from 1918, cost approximately $230 in inflation-adjusted 1943 currency. The Quonset's superior comfort and electrical systems justified the higher price in American procurement doctrine, but that 300% cost increase mattered significantly when multiplying across thousands of units. The total American expenditure on Quonset production exceeded $140 million by war's end. Production volume numbers told competing stories about success. The United States manufactured approximately 170,000 Quonset huts between 1941 and 1946, an average of 34,000 per year. Britain produced roughly 100,000 Nissen huts just during World War I, between 1916 and 1918, averaging 50,000 per year, with far less industrial infrastructure. The difference wasn't manufacturing capability, it was design complexity. Nissen huts required corrugated steel sheets, basic fasteners, and rough timber. Any sheet metal facility could produce components. Quonset huts needed specialized steel forming for the arch ribs, precise die cutting for panel mounting holes, and coordination between insulation suppliers, electrical component manufacturers, and lumber mills. The engineering trade-offs became most visible in adaptability. After initial construction, Quonset huts could be upgraded. Crews could add partition walls, install heating systems, run additional electrical circuits, mount heavy equipment to the steel framework. These capabilities made them suitable for permanent installations, like stateside training bases and rear echelon headquarters. Naval Air Station Alameda in California received over 400 Quonset huts in 1943 that served as workshops, classrooms, and administrative offices. Many remained in use until the base closed in 1997, some for over 50 years. That longevity validated the American approach for installations where permanence mattered more than construction speed. But the framework that enabled those upgrades became a liability in temporary field use. When the 43rd Infantry Division moved from Guadalcanal to New Georgia in June 1943, they couldn't disassemble and transport their Quonset huts. The steel ribs, once bolted together, were difficult to separate without damaging threads. The screwed-on panels could be removed, but without the framework, they were useless. The entire camp infrastructure, 42 Quonset huts, stayed behind, abandoned. Nissen huts disassembled almost as quickly as they erected, because the bolted panels separated cleanly and could be reused elsewhere. British forces routinely relocated Nissen camps, moving the same structures from Egypt to Italy to Greece as front lines shifted. Here's what this all comes down to. 2 different countries, 2 different philosophies, 2 different wars they were preparing to fight. Britain, in 1916, was bleeding to death. They needed shelter immediately. While shells were falling, while men were dying, they needed something so simple that exhausted soldiers could build it in the dark, with minimal tools, using whatever materials happened to be available. Speed was everything. Comfort was nothing. America in 1942 was the richest country on Earth, with the largest industrial capacity in human history. They weren't fighting for survival, they were fighting to win, and win permanently. They assumed bases would be occupied for years, that supply lines would be secure, that construction could happen without enemy interference. So they made the Nissen better, added insulation, added electrical systems, added proper floors, added structural frameworks that would last decades. They turned emergency shelter into permanent architecture. And in doing so, they made it slower to build, more expensive to produce, more complicated to deploy, less adaptable to field conditions. The Quonset was objectively superior in every measurable way except the one that mattered most in combat: getting soldiers out of the mud and into shelter before the next bombardment started. This tension between optimal and adequate appears throughout military history. The M1 Garand rifle was superior to the bolt-action Springfield in every measurable way, but it was also heavier, more complex, required more maintenance. Sherman tanks were mechanically reliable but under-armored compared to German Panthers. American forces won with adequate equipment deployed in overwhelming numbers rather than perfect equipment deployed slowly. The Quonset followed this pattern. It was better shelter than the Nissen, but armies needed shelter faster than they needed it better. When the 1st Marine Division was fighting in Guadalcanal mud during late 1942, having a weatherproof structure in 3 days would have mattered more than having an insulated electrified structure in 10 days. The fundamental lesson embedded in the Nissen versus Quonset story is that military logistics doesn't always benefit from engineering improvement. Peter Nissen created his hut by asking one question: what's the absolute minimum needed to keep soldiers dry and alive? His answer? Curved, corrugated metal bolted together. That's it. No foundations, no framing, no skilled labor required. Just metal sheets and bolts. That ruthless simplicity meant a sergeant and 5 exhausted infantrymen could build shelter in 72 hours while under artillery fire. The American engineers who designed the Quonset asked a different question: how can we make this more comfortable and permanent? Their answer was objectively better architecture, but practically worse emergency shelter. After the war ended, the two designs had completely different fates. The United States military found itself with approximately 70,000 Quonset huts scattered across domestic bases that were rapidly closing. The War Assets Administration began selling complete Quonset huts to civilians in 1946 for prices between $200 and $600. That same year, over 15,000 Quonsets were purchased by farmers, small businesses, and housing-desperate families across America. The huts' integrated floors, insulation, and electrical systems made them immediately habitable as homes, workshops, or storage buildings. Drive through rural Iowa, Kansas, or Nebraska today, and you'll still see Quonset huts serving as machinery sheds and grain storage. Small airports across the Midwest used them as hangars through the 1970s. The University of Illinois housed returning veterans in a Quonset village from 1946 until 1972. 260 huts providing temporary family housing that became semi-permanent because nothing replaced them. These structures succeeded in civilian use precisely because of the features that slowed their battlefield deployment. The insulation kept them comfortable year-round. The strong framework supported shelving, equipment hoists, and modifications. The finished interiors accepted drywall and paint for those wanting conventional appearances. Britain took the opposite approach with Nissen huts after 1945. The military wanted them gone because they symbolized wartime austerity. Thousands were dismantled. The corrugated panels sold as scrap metal during the post-war steel shortage. Some found civilian use. Farms in Yorkshire and Scotland converted them to sheep barns and equipment storage. But the British government actively discouraged civilian retention, because they wanted to distance national identity from wartime temporary architecture. By 1955, most Nissen huts had vanished from Britain, except on remote military ranges and agricultural properties where practicality outweighed aesthetics. The 170,000 Quonset huts America produced represented genuine industrial achievement. They provided shelter for millions of personnel across every theater. They served well in their intended role as semi-permanent base infrastructure. But they couldn't match what 6 British soldiers accomplished in 1916, building weatherproof shelter in 3 days with nothing but hand tools and determination. That capability, that speed, that brutal simplicity was the actual innovation. The Quonset improved everything about the Nissen except the one thing that mattered most in combat: getting soldiers out of the mud and into shelter before the next bombardment started. The corrugated curved huts still standing across farmland and former military sites are monuments to different philosophies. The surviving Quonsets prove American engineering made them durable enough to outlast their intended purpose. The vanished Nissen huts proved British engineering made them simple enough that armies could build them anywhere, anytime, under any conditions, and then abandon them without regret when the front lines moved forward. Both approaches worked, but only one could be built while the shells were still falling. And that's the difference between architectural success and battlefield necessity.